What's up, everyone? Welcome back. This video is part 2 of 7 for the free FAA Part 107 series, Drone Certification 2026 to 2027. We'll be covering everything that has to do with air, AIR. For example, airspace, airspace classifications, airport operations, airport runway headings, air traffic patterns, airplane dynamics, airplane control surfaces, air density, density altitude, and a question that I really didn't expect that surprised me on the Part 107 exam was how does a pilot determine wind direction when landing a plane based on Smokestack Plume? Now, I bet you didn't see that one coming, did you? But we're going to be covering that and much more in this video. Are you ready? Let's go. Now, before you can understand about airspace classifications, you first need to understand about what airspace actually is. Under 14 CFR Part 1.1, it doesn't specifically state airspace, but it does mention about navigable airspace as a portion of the sky that an aircraft can legally be allowed to operate. And within this portion of the airspace, there are altitude limits. Now, these restrictions are set in place primarily for the aircraft during takeoff and during landing. There are two types of airspace that you need to be concerned about. The first is controlled airspace, and the second is uncontrolled airspace. Now, according to 14 CFR 1.1, airspace is defined as the dimensions within a certain airspace where air traffic control can provide a service. I bet you didn't understand that definition before, right? You see, air traffic control controls all of the controlled airspace. See how funny that sounded? So to put this very simply, airspace is the portion of the atmosphere above the Earth that is regulated for aircraft operations. In other words, it's the sky that aircraft and drones fly in, and the FAA divides this airspace into different sections so that way traffic can be organized and kept safe. So now that you understand that, let's talk about the different classifications of airspace that you'll need to know for the Part 107 exam. Now, looking at this chart that the FAA provides, do you see how there's Class A, Class B, Class C, Class D, Class E? There's no Class F, but there is a Class G, which is uncontrolled airspace. We'll talk about that in just a minute. Think about all of these as giant shopping malls. And the biggest shopping mall that you see is the one directly above Class A. That is just a huge shopping mall. And the only way you can get to that shopping mall is by taking a hot air balloon and going all the way up to 18,000 feet MSL. Class A airspace, the one that you're seeing in red, starts at 18,000 feet MSL and will go all the way up to where you see it says FL 600. Remember when I said that you have to add 2 zeros? Well, that's FL 60,000 feet. This is only for commercial airliners, and don't worry, you won't see this on the Part 107 exam because the FAA knows that you're not going to be flying in that airspace. Class A airspace covers the entire region of the North Atlantic United States. Now let's drop down just below. What is underneath Class A airspace? And immediately you're probably going to think, well, there's Class B airspace that's right below it. No. What is directly below Class A airspace is Class E airspace. Think of this for a moment to help you remember. Class A airspace is the airspace above Class A, above all others. Class E airspace is the airspace that is everywhere. Class E airspace can begin at the surface, or it can begin at 700 feet AGL, or it can begin at 1,200 feet AGL, above ground level, or it can begin at 14,500 feet MSL. Now, do you notice how I made the clear distinction that Class E airspace can be measured in both AGL and MSL? Pretty amazing, huh? Class E airspace is the most difficult to comprehend, to understand, because of the fact that there are so many different variables. But we're going to explain it so that way you have a clear understanding. Always remember this. The altitude limit for Class E airspace is 17,999 feet MSL. And that's why you'll hear the phrase up to but not including, because if it went 1 foot higher, it would be 18,000 feet, and that means it would be Class A airspace, not Class E airspace. Moving to Class B airspace. Bravo. Learn those phonetics. You're going to need it. Class B airspace is where you will have the biggest airports with the busiest traffic, and you'll see multi-layers of airspace as you're looking at with the yellow Class B, where you have an interior layer or an inner core, then you have a shelf above that with some airspace, and then you have another shelf above that. We're talking about a lot of controlled airspace here with a lot of planes flying in and out. And although it looks as though it's close to Class A airspace, which begins at 18,000 feet, no. Class B airspace will extend to its limit up to 10,000 feet MSL. So stop and think just for a moment. If you know Class B goes up to 10,000 feet MSL and Class A begins at 18,000 feet MSL, there has to be something in between, right? Well, you know what that is. The only airspace that is everywhere, Class E airspace. Now, on a sectional chart, Class B airspace will be depicted by solid blue lines. Notice how the word blue begins with the letter B for Class B airspace. This is figure 25, Dallas-Fort Worth International, a very busy Class B airport. Now, some of you Sharpies, I already know that you noticed something, that this particular Class B airspace has a vertical limit of 11,000 feet, when I just finished saying that Class B airspace will extend up to 10,000 feet. Why is this one saying 11,000 feet for Dallas-Fort Worth International Class B airspace? And that's an easy answer, because this particular airport has a huge number of arrival and departures, so they need an additional 1,000 feet of Class B airspace in order to accommodate the heavy traffic. It's one of the busiest airports in the world. But anyway, what I want you to pay attention to on this sectional chart is that the solid blue lines will indicate where these layers are. Notice that the inner core around the airport runways is telling you that it begins at the surface and will go up to 11,000 feet MSL. Pay attention. Notice that there are outer layers also, like you saw with the upside down wedding cake, as they call it. But notice how there are more than 3. Before, when we were looking at the diagram, there were only 3 layers, right? But if you pay attention to figure 25, you will see more than 3 layers on this Class B airspace for Dallas-Fort Worth. Now, let me expand your thoughts, expand your vision here for what it is that you're looking at. All of these layers for Class B airspace are hanging over all of these other little airports, meaning it's sort of like an umbrella that's over all of these other little Class D airports. And as you can see, what's directly above those Class D airports are the altitude limits of Class B airspace hanging over, which the floor of this Class B layer will begin at 3,000 feet MSL, and the ceiling of that layer will be at 11,000 feet MSL. Okay, moving to Class C airspace, which is for the more conventional airports, the city-type airports, not as big as Class B, but still taking in airport traffic in the way that a conventional airport would. Class C will have 2 layers of controlled airspace, an inner core where the airport is located at the surface, and then directly above that will be an upper tier or upper shelf where the airport traffic will be expanded outwards. Now, on a sectional chart, you will find that Class C airspace is indicated by solid magenta lines. Notice that there is a small inner core, and then around that will be the outer core that expands outwards at a much greater distance in nautical miles. And just so you know, Class C airspace will begin at the surface and extend up to 4,000 feet MSL. And question, what is above Class C airspace? Well, it's the only airspace that is everywhere, Class E airspace. Now, since I'm primarily talking about Class C airspace, but I'm also mentioning Class E airspace, It's a good time in the video to tell you about Class E Airspace when it comes time to looking at a sectional chart. And you do remember that I said Class E Airspace can begin at different altitudes. Well, let's go over that right now. And the best way to teach you this is to show you and then tell you. Do you remember show and tell when you were a kid? Of course you do. I'm going to point to a certain location and tell you what the altitude is for that and what class of airspace it is. I'm pointing to a faded magenta boundary around an airport, and that means that Class E airspace will begin at 700 feet AGL. And you can see there are quite a few faded magenta in this area, right? I'm pointing to a solid magenta line, and this is the outer core or the outer layer of Class C airspace. And what is the altitude limit for this outer layer? Well, it's already indicated on the sectional chart with a 47/20. So it's 4,700 feet MSL will be the vertical limit. Now here's a question that you should already know the answer to. The floor of that outer layer of Class C airspace begins at 2,000 feet MSL. What is the airspace that's directly below that outer layer? Keep in mind that there is a faded magenta boundary that's completely around that Class C airspace. And what does that mean? Let me tell you. Anything inside of that faded magenta boundary that you're seeing is Class E airspace beginning at 700 feet AGL. Now I drew a diagram here so you'll have a better understanding. See the surface where the airport runways are? That's Class G. Anything outside is Class G airspace. But as you go up into the faded magenta, starting at 700 feet AGL, that will be Class E airspace. It's a transition zone for aircrafts that are arriving or departing from the main airport, and it will be Class C because those are solid magenta lines on the sectional chart. Now you see the floor of the outer layer at 2,000 feet MSL, and then as you go up to the upper limit at 4,700 feet MSL, you can see it very clearly as I indicated on this drawing. Now going back to the sectional chart, do you now see how it's beginning to make sense in regard to Class C airspace, its limits, and Class E airspace and its limits? Now, here's another question I need to ask you to keep your brain thinking, to keep your brain working. Class E airspace, is it controlled airspace or is it uncontrolled airspace? I mean, look at it. It's everywhere. How is it feasible or even possible that air traffic control will be able to maintain control of such a large area of airspace? And a lot of you are probably scratching your heads, but this is actually a great question because it gets to the heart of knowing Class E airspace and how it actually really works. You see, Class E airspace exists primarily so that air traffic control can control IFR aircrafts or aircrafts flying under instrument flight rules. It's not necessarily set up in a way where they can control every single aircraft flying within that particular airspace. So the answer to the question basically comes down to this. Even though Class E airspace exists across a large portion of the country, air traffic control only needs to maintain separation between the aircrafts that are flying under IFR, instrument flight rules. To put this very simply, if an aircraft is flying with instruments, they need to be controlled by air traffic control. Air traffic control needs to speak with them. They need to talk to each other. But when an aircraft is flying under visual flight rules or VFR in Class E airspace, they're usually operating on a see to avoid basis or see to avoid rules. So they don't need to or they are not required to talk to air traffic control. So imagine if an airplane is hundreds of miles away from the airport. Well, if they're flying in Class E airspace and they're flying IFR, then air traffic control will need to separate them so that way they are safe. And if they're flying hundreds of miles away from the airport and they're flying under visual flight rules, they don't need to speak with air traffic control despite the fact that the airspace that they're flying in is still controlled airspace, Class E airspace. So you can see how Class E airspace is very complex, and there are also some other complexities such as the faded magenta magenta colors that you will see, or the faded magenta boundaries that you'll see on a sectional chart, and that indicates that Class E airspace begins at 700 feet AGL. Now, you will also see a dashed magenta line that indicates that that is also Class E airspace around the airport, but a dashed magenta line around an airport indicates that Class E begins at the surface, not at 700 feet AGL like you saw with the faded magenta. Now, I want you to understand the three different scenarios that you have with Class E airspace. The first is when Class E airspace begins at the surface. This is indicated, as I mentioned, by the dashed magenta line around the airport. It starts at the surface. You will always need authorization from air traffic control when you see a dashed magenta line Class E airspace beginning at the surface. Now, if you see an airport that has a faded magenta boundary around it, that will start or begin at 700 feet AGL. Class E airspace with a faded magenta will begin at 700 feet AGL. Now, what is so significant is that you already know that you can only fly 400 feet AGL, or 400 feet above the ground, right? So therefore, you don't have to worry about the 700 feet where Class E airspace begins with the faded magenta, because you're only flying 400 feet above the ground. That's the only thing that the FAA is going to allow you to do, 400 feet AGL. But there are situations where you have to go over 400 feet. Let's say you're flying over a tower, or you need to inspect a tower. Then you can fly over 400 feet, right? So that means that it's possible that if the tower is 400 feet, you can fly 400 feet above that tower. That will put you at 800 feet. And that means that you are 100 feet above Class E airspace faded magenta, which began at 700 feet AGL. Do you get that? You're 800 feet above ground level flying in Class E airspace. So the question here is, do you need authorization to fly in Class E airspace since you are 100 feet above where Class E airspace began at 700 feet AGL? The answer to that question is no. You do not need authorization to fly in Class E airspace at 700 feet AGL faded magenta. And the reason for that is because when you initially launched your drone, it took off in Class G airspace, and you do not need authorization for Class G airspace. So as you were ascending or flying upwards, you met Class E airspace at 700 feet AGL, and then you went above that another 100 feet to 800 feet AGL, and the FAA says that the only time that you need authorization in Class E airspace is when Class E airspace begins at the surface, the dashed magenta line that you see on the sectional chart. This is something that has been confusing many of you, so just remember, if Class E airspace does not begin at the surface, you do not need ATC authorization to fly. Now keep this in mind, a faded magenta boundary will begin at 700 feet AGL, but what about the scenario when you don't have a faded magenta boundary, you don't have a dashed magenta line, and it's just airspace that's just there? What is the classification of that airspace? Well, here's the thing. If it's not marked, it's not labeled, there are no colored lines, no boundaries, it doesn't give you a specific reference to airspace classification, you don't know what it is, it's just airspace that's there, then that means that it will be Class G airspace up to a certain altitude. You see, anywhere that is not labeled or marked or referenced as controlled airspace will be Class G airspace, uncontrolled airspace, and Class E airspace will begin at 1,200 feet AGL. Now, if you see a faded magenta boundary anywhere, that airspace will be considered as Class E airspace beginning at 700 feet AGL. But for all intensive purposes, remember that Class G airspace is directly under Class E airspace until you get to a certain altitude. Now, the only airspace that I have not discussed is Class D D, Delta Airspace. You see, Class D is a little bit different than the others, and I'll tell you why. On a sectional chart, it is the only airspace around an airport where the pilots will be able to identify it quickly because they will usually have a dashed blue line with a little box and a number inside of it. Pilots know that when they see that little box with the number inside of it, that is Class D airspace. It's a quick identifier for pilots to know where Class D airspace is on a sectional chart. Now, very important, when we're referring to Class D airspace specifically on a sectional chart, it will always be referenced in MSL. And the usual altitude limit for Class D airspace will be at 2,500 feet MSL, give or take, because depending on the airport elevation, that might be a little bit more or a little bit less. But you will know what that is. All you have to do is just to look at the little blue box with the number inside of it, and that will tell you the altitude limit for Class D airspace. Okay, so now that we've talked about airspace in this air series, let's talk about airport runways. Now, this is something that pilots are always able to see, but most people do not fully understand about airport runways. You see, the numbers that are painted on an airport runway, if you have ever looked at an airport from above, or even just seen them in a photo, you'll notice that there are big, white, large numbers at the beginning of each runway. And you know, they don't just paint these numbers on there randomly and just say, hey, you know something? This looks like it could be runway 36, so let's just paint a 36 on this one, and let's paint a 34 on that one. Let's paint a number 8 on that one. They don't do that. All of those numbers are there for a specific reason, and the reason is because each and every number that you see on a runway has to do with a direction, a magnetic direction, or a magnetic heading. These numbers are there to help the pilot when the pilot is flying at distance away from the airport. They're able to navigate appropriately with their instruments because the instruments will tell them what direction they need to be flying in to line up to the appropriate runway that they're getting ready to land on. And as simply as I just explained that, it is a very difficult concept to understand if you're not an active pilot actively landing on a runway. So here's the thing. Runway numbers represent the magnetic heading of the runway by degrees, and it is rounded to the nearest 10 degrees. Okay, so now we're going to be talking about something that I promised you in the intro, and that is about smoke flume. Now, little birdie told me that this question has been coming up repeatedly on the Part 107 exam, and you're going to see a picture of smoke, but you won't understand what exactly it means because there's been no explanation and no references that you could study from until now. And this is part of the air series because it has to do with stable air, unstable air, and natural air in regard to smoke flume. And this question is something that if you do not understand it, you won't get it right. You'll miss it. So here it is. The question that the FAA is asking is not actually about smoke. It's about testing atmospheric stability. Let's begin by breaking this down. A smoke flume is just a visible clue. You see, if you're flying an aircraft or an unmanned aircraft, such as a drone, then when you see a smoke flume and the smoke happens to be looping or bouncing up and down, or it's acting in a chaotic way, or it's just looking like it's crazy, that means that the air around that smoke is unstable. That's the first thing that you need to remember. The air is unstable. And there are 3 types that you must know about. The first is unstable air when you're looking at a smoke flume acting crazy. Now, the reason for that is because warm air is rising and shrinking rapidly. This creates turbulence, updrafts, downdrafts, and that's why you're seeing the smoke acting in that manner. It's usually exactly what happens on a hot, sunny day when the strong vertical motion exists in the air, making it unstable. Now, for the second one, when you see the smoke is spreading out in a cone-shaped manner, it's not acting crazy, it's not wild, and it's not too flat. It just has a natural cone shape to it. This usually usually occurs whenever you have overcast skies and steady winds. The air is balanced. It's not rising too much, but it's not shrinking too fast. It's called a natural air, and this natural air is called coning. Now, let's go to the third and last one, will be when the smoke is flat and it's spreading out in a horizontal manner, almost like a horizontal line. The air is stable and there's little vertical movement, often during temperature inversions, and you'll notice that the smoke can travel far without rising. The condition that you have in this scenario is stable air. There's no vertical movement. There's no turbulence. There's no psychotic craziness that's happening in its behavior. It's just moving still. I like the way I said that. Now, here's where we get to the part where I'm going to ask you a few questions. I know you like this. You observe smoke rising from a smokestack that rises briefly and then spreads out horizontally in a thin layer. What does this indicate about the atmospheric conditions? Now, you see A, B, and C answers, right? I know you're picking the one that is correct. You should know it because we just went over this, right? But the answer has already been provided in the question. And the question basically is telling you that we're dealing with stable air with little vertical movement because it's traveling in a horizontal thin layer spreading out, and there is no movement. So the correct answer is C, stable air with little vertical movement. Now, the FAA also has some information on flumes in their Potential Flight Hazards publication, and you'll be able to look through it. Just click on the Resources tab on my website. Now, what they're saying here is that a pilot should stay clear from exhaust flumes when flying on the upwind side of a smokestack or cooling tower. And it's amazing that I'm using these words and terminology because you already understand this when we were speaking of airport traffic patterns in regard to the downwind leg and flying upwind. In this situation, when the smoke leaves the stack and it's being carried away, the direction that it's being carried away is the downwind side. So where you need to be flying your drone as a remote pilot is on the upwind side. And what I do is just simply to draw an invisible line on that smokestack mentally, so that way I know which side I'm supposed to be oriented on. Anything on the other side of that line closest to the wind is upwind, and anything that's on the other side of that line is downwind, so I stay clear from that area. These are the things that the FAA wants to test you on. They want to know if you're familiar with it, and you'll be able to connect the dots appropriately simply by watching these videos and going to my website. Now, they also mention about visible smoke flume and invisible smoke flume. So let's talk about this. A visible smoke flume is exactly what it sounds like. The smoke is something that you can see from a source, such as a smokestack or an industrial plant. It's an indicator that allows you to determine the wind direction and whether or not the flume is blowing downwind. It also provides you with an approximation of the wind speed. Very important here, huh? Because when the wind is light, then the flume rises and slowly drifts. But when you have a strong wind, the flume bends and it twirls and it flattens. And you develop this understanding by experience, and in turn, it sharpens your instincts as a remote pilot. Pilots who are flying manned aircrafts, well, when they see smoke blowing across a runway, well, that's the indication of the surface wind direction. So visible flume provides a lot of information. So what about invisible smoke flume? Now, this is where everything gets interesting. An invisible flume is still flume. The only thing is that you just can't see it. And you know how I like to give you these analogies so that way you have full understanding, right? Think of it as heat. You can't see heat, but sometimes you can see the effects of heat. For example, let's say you and I are walking in a desert and we look all the way in the distance and we see this kind of shimmering mirage effect. It looks like some sort of distortion that's rising off the surface. Well, that's heat. And even though we can't see heat, we can see the effects of it. And that's what I'm referring to with invisible flume. So the FAA wants you to understand something. That invisible flume is much more dangerous, and I'll tell you why. It's because you can't see the wind shifting. You can't determine the turbulence, and you misjudge misjudge your direction entirely simply because of the fact that you don't know whether you're upwind or downwind. Just because you see a smokestack that does not have visible smoke coming from it doesn't mean that you're safe. Experienced pilots already know that just because they're approaching a runway, it may appear to be calm, but an invisible flume could mean that there's going to be crosswind that exists. There's going to be wind shear that's present. There may be turbulence that's developing. These are all things that experienced pilots already know. And the key takeaway here that you now know is that a smoke flume, either visible or not, is simply a movement of air that's being revealed or not being revealed. Now, before I get to another question, let's talk about a smokestack flume used as a wind direction indicator. And a lot of you that have already taken the exam can back me up because this question was on the exam. A smokestack flume does not only just indicate air stability, it also indicates wind direction. Common sense and observation alone will allow you to understand that smoke will usually drift with the wind. So to put this like a poet, the direction that the wind is blowing is the direction that the smoke is going. And let me back this up by asking you a question. How do you think the FAA expects you to think about this topic, about this question? Well, let me put you to school on this one. You see, if the smoke is blowing towards the east, that means that the wind is coming from the west. And did you notice how I just said wind is coming from the west? Because that is something that you need to remember in regard to aviation. In aviation, the wind direction is always named for where it is coming from, not where it is going. So a typical FAA bear trap question, because they want to make sure that you understand it, right? They will ask you something such as this. A smokestack with smoke blowing to the right, what direction is the wind? The correct answer will always be that the wind is coming from a certain direction. If you've ever listened to an official NOAA weather broadcast, a weather report, it will always say the wind is coming from. Coming from are the key words that you must always remember. So now that I've given you all of this smoke flume information, let's go back to what I mentioned at the beginning of the video in the intro. You see, pilots will use a smoke flume to determine the wind direction, which directs them and tells them which runway they need to land on. The rule of thumb for landing is that an aircraft must always land into the wind or land into the headwind. The reason for that is because it lowers the ground speed whenever you have a headwind, and it gives the pilot better control. And more importantly, what it does is when you're landing into the wind, it allows you to land with a shorter distance of travel. And a lot of you just had a wake-up moment because now you understand why an airplane can land on a very short runway. So putting this all together for the Part 107 exam as to why a pilot can use a smokestack flume as an indicator to land a plane, you see, a smokestack flume will tell you where the wind is coming from. So therefore, the pilot understands that the wind is coming from a certain direction. So if the wind is coming from the north because the smoke is blowing to the south, then the pilot will use that information, that indicator, to land the plane flying towards the north. Okay, let's talk about airport traffic patterns. Now, what is an airport traffic pattern? Well, it's sort of a rectangular path in the sky that planes fly, kind of like if you're at a fast food restaurant and you're at the drive-thru and all the cars are in front of you and there's some cars behind you, but everyone seems to be making these left-hand turns around the building to eventually get to the checkout window. In this case, all of the planes are flying and following a similar pattern. It's a standardized collision avoidance system that has been implemented so that way there's safety involved whenever it is that you have planes arriving and departing an airport. Now, there are two things I want you to remember offhand about traffic patterns. The first is that traffic patterns are usually 1,000 feet above the ground, 1,000 feet AGL. This is an important piece of information, don't you think? Because if you're operating and you're flying a drone that's about a mile away from an airport, well, These traffic patterns can be a mile away from an airport, meaning that there will be aircrafts that are flying at 1,000 feet AGL. And you don't want to be the remote pilot that just happened to be inspecting a tower a mile away from an airport, and then you're flying and you come very close to an aircraft that is attempting to enter into a traffic pattern, trying to land their plane at the closest airport. Now, realistically, the probability of that scenario actually occurring is next to nil, because you have to get authorization if you're anywhere close to an airport anyway. But it's good to keep these things in mind, because sometimes we happen to just be flying our drones and not thinking about the fact that we need to get authorization. Now, the second thing that I want you to remember is that these traffic patterns have what's called legs. And the legs are sort of like a relay team. You have the first leg, second leg, third leg, fourth leg running the race. But in this case, all of the legs in the traffic patterns have names. So let's go over them so you're familiar with them for the Part 107 exam. The first of 5 legs is called the upwind leg, and this leg begins immediately after takeoff. The aircraft will lift off of the runway and then climb straight out on the runway heading. Do you see how this is all coming together? Because I'm using terminology, runway heading, where you're already familiar with that from the previous section that we had in this video. The upwind leg is where the pilots will stay aligned with the runway and fly straight out to avoid any conflict with other aircrafts. Now, I'm going to go a little deeper because this is one of the most underexplained legs, and understanding this properly gives you a big edge. The upwind leg is an extension of the airport's runway as the aircraft is lifting off. And what confuses people the most is that the aircraft is typically taking off into the wind on the upwind leg. Now, the reason that I just pointed that out to you is because you remember me saying previously before that the aircraft will be landing into the wind. And some of you are saying, how is that possible? Well, it is, because the aircraft that is taking off into the wind on the upwind leg will be expecting that there is another aircraft directly behind them that will be landing from the final approach leg. Both of them, departing and arriving, will be landing into the wind. Now, let's go a little deeper so I can tell you why this is so advantageous on both counts. You see, when a plane is taking off into the wind, meaning that the wind is coming towards the aircraft, it allows the wings of the aircraft to ascertain or develop more lift. The more air that an aircraft's wing will have around it will develop more lift, so the aircraft will be able to take off much faster. And the plane that is landing behind it also will have wind coming towards it, and that will create drag, so therefore the plane will slow down much easier. Now, on the upwind leg, a pilot will usually turn 90 degrees into what's called the crosswind leg, but in actuality, it won't be a full 90 degrees. You've been on a plane before when you see that the plane is turning and they're not actually making a complete left-hand turn. The pilot is partially utilizing the wind, so that way he or she can maintain altitude, can maintain lift. The crosswind leg is the one that's perpendicular to the runway, and the reason this leg is so important is because it allows the aircraft to have separation from other aircrafts. But more importantly, what it does is that it leaves the aircraft in a position where it does not completely leave the area of the airport. You see how the pilot has options for departure. It can either be a 40-degree departure or it can be a straight out departure. Notice that the pilot also has an option to make a 90-degree turn into the crosswind leg. Now, this is a huge benefit for the pilots because if something goes wrong with the aircraft, the pilot then has an option to get back into the traffic pattern and prepare for landing. As you can see, we're making a left-hand turn, not so much a 90-degree turn, but towards the crosswind leg, so that way we can resume on a heading that will take us away from the airport traffic and towards towards our destination. Now keep in mind that some airports have right-hand traffic patterns as well. Now at the end of the crosswind leg, making another 90-degree turn, you will come to the downwind leg. And this is a very important leg. I'll tell you why. It's because when an aircraft needs to enter or join into a traffic pattern, the place at where they will enter into the traffic pattern at a 45-degree angle will be the downwind leg. Now, very important, what I'm about to tell you. The downwind leg will be parallel to the runway and flying in the opposite direction as the planes that are taking off and landing. This is something that you're going to need to remember for the Part 107 exam, because when they ask you what direction is the plane heading in if it's traveling downwind, you know the direction that it's traveling in because it's traveling opposite of the runway. And do you now see the logic behind me explaining to you the opposite ends of the runway so you understand the headings by degrees? If the FAA is telling you that the plane is on the downwind leg of runway 18 and they're asking you what direction is the airplane heading, you know that answer because I taught you well. The aircraft is heading in a northerly direction. It's heading north. And I know a lot of you just jumped out of your seat and you just said, I got it. This is why I'm so excited about explaining this to you in this way. So go ahead and hit that like button, okay? Boost up that algorithm. Another thing that you need to remember about the downwind leg is that the wind will be blowing in the same direction, meaning that the wind is at our backs. So when the aircraft finally comes to the end of the downwind leg, it will make another 90-degree turn, and that will put it on what's called the base leg. And you're probably asking yourself, how many legs does this thing actually have? Well, anyway, once you're on the base leg, this is where you're starting to orient yourself. You're starting to see the airport on the left side of your window. Things are starting to line up a little bit, so you're getting yourself oriented to get to the final leg so you can line up with the runway. At this point in time on this base leg, you're reducing the altitude. It's continuing to slow down even more, and it starts aligning itself for final approach. You haven't gotten to the final leg yet, but you are transitioning from a flight level to a lower level, descending so that you can get onto the final leg, which is, appropriately speaking, the final approach leg. Now, one last 90-degree turn from the base leg onto the final leg will line the aircraft up to the runway center line. The aircraft is continuing on a controlled descent in order to land. At this point, the aircraft is fully configured for landing. Flaps up, wheels down, speed is set, and the pilot is focused on the alignment and the glide path for smooth landing. And after touchdown, it will then coast and taxi off the runway so that the other aircraft behind it can do the same exact thing. So now that we've talked about the airport traffic patterns and we just briefly touched on the flaps and the wheels down, let's talk about the aircraft control surfaces, which you'll need to know for the Part 107 exam. Now let's start off this segment by asking a question, as we always do. What exactly is a control surface of an aircraft? Control surfaces are the movable parts of an aircraft's structure that the pilot uses to control its direction and attitude during flight. Now, this is not like the steering wheel that you have on a car. This is something that changes the direction of the airflow by using hinged surfaces such as flaps. And these movable flaps ultimately change the aircraft's movement. Now, the FAA wants you to know the names of these control surfaces, but they also want you to know how these control surfaces affect the 3 access points that are on an aircraft. We're going to be discussing this right now. First thing that you need to know of extreme importance is that every single aircraft will move on 3 access points. And I'm going to explain this to you so that way you understand it with complete comprehension. The first access will be a longitudinal access that runs from the nose to the tail. Now, I want you to imagine that there is a string that is is coming out of the tail and a string that is coming out of the nose, and we're pulling that string so tightly that the aircraft is still, it's balanced. But if we twist the rope a little bit, you will see the aircraft's wings will begin to move up and down. This is what's called roll on a longitudinal axis. But there is a way to simulate this roll in the same exact way without the rope or without the string. And all we have to do is to have the flaps on the wings adjust themselves either up or down, so that way it will simulate the same exact effect on a longitudinal axis, and this is called roll. Now, the flaps on the wings that I just referred to are called ailerons, and the ailerons are what control the roll of an aircraft. And you're beginning to understand why they call them control surfaces, right? So now that you understand how we control the wings to move them up and down, side to side, let's talk about another axis, and this is called the lateral axis. Now, I want you to take that same string again, but this time we're going to put it through one side of the wing and put the rope or the string through the other side of the wing, and we're going to pull it very tight. The aircraft is now stable and it's not moving. But if we twist the rope in either direction, the nose of the aircraft will either go down or it will go up, or the tail of the aircraft will either go down or up, depending on how we're twisting the rope from the side of the wings as we're pulling it and twisting, right? Do you understand that? The rope that is coming out of the wings on each side is on a lateral axis, and it controls the pitch of the aircraft. When you see the nose going up and down, that is controlling the pitch. Now, let me ask you, what control surface do you think will be controlling the pitch of the aircraft? Some of you know it and some of you don't, but I'm going to tell you anyway. There are two little flaps on the back wing of the tail that move up and down. And if you can imagine that as they're moving up and down, it's controlling the nose moving up and down also. It's controlling the pitch of the aircraft to either move up or down, so that way the airplane will either climb or it will descend, depending on what you're doing with the little flaps on the tail. Those flaps are called elevators, and they're both connected together. They both move at the same time in the same direction, same place. They're both connected and locked, so that way whatever angle they're set at, both of them have the same exact movement at each time. So they're called the elevators, and they control the pitch. And don't forget, the pitch is always referenced to the lateral axis. Now let's talk about the vertical axis. Let's go ahead and take the same rope again, and this time the rope is coming out of the top of the aircraft and then also coming out of the bottom of the aircraft, and we're pulling it very tightly so the aircraft is still, and then we're twisting it. In which direction do you think the aircraft is now moving? Correct. It's moving from left to right. The nose is actually moving from left to right as we twist the rope. Is that right? So that is called the yaw. So whenever you see the nose moving from left to right on a vertical axis, remember the rope, that is called the yaw. So what do you think would control the yaw? Well, it's the same thing that would control a boat or a ship. It's called the rudder. And the rudder is that tail fin that's sticking up in the air that has a little flap on the back of it, and that is called the rudder. And any time that that rudder moves from left to right, it will also manipulate the nose to move left and right also. So do you see how you have all of this information broken down? So it's very clear to understand that you have a longitudinal axis, you have a lateral axis, you have a vertical axis, you have pitch, roll, and yaw. And all of these things combined is what allows the aircraft to be able to fly and be manipulated by the pilot in command. Now, just so you know, the aircrafts will also have what's called stabilizers They're much smaller little flaps, and they're used to stabilize the aircraft in a way where the air is being manipulated slightly, not majorly. But for the Part 107 exam, the three primary control surfaces that I just mentioned to you are what you need to pay attention to, because those control surfaces you will find on a Part 107 question. Now, the last thing I want to discuss on this air series are two things that are very confusing. The first is air density, and the second is density altitude. Now, I know a lot of you just perked up, because if there are two things that have the most amount of difficulty in regard to explanation, it would be these two. But I am going to do my best to break this down so you have maximum comprehension, and hopefully by the end of this video, you'll walk away with something that you didn't have before. And there's something that is very profound that was once told to me that I will never forget. So let me pass this on to you. Most pilots don't crash because they don't know how to fly. They crash because they don't understand the air that they're flying in. And that profound statement brings you halfway to the point of understanding this whole thing about air density and density altitude. So let's start by asking a simple question. What is air density? Well, air density is just how thick or thin the air is. That's it. If the air is thick, your aircraft performs better. If the air is thin, your aircraft performs worse. That's it. And what controls the thickness or the thinness of air density? Well, there are only three things: temperature, pressure, and humidity. That's it. Do you see how easy that was for me to explain to you? But I already know that even after that simple explanation, that your head still can't grasp the concept, because it's a complicated topic that I need to break down in its simplest form. Let's start with temperature first. When temperature goes up, the air expands and the molecules spread out. The air becomes less dense, so hot air equals thin air. You ever find that when it's hot out that you have a difficult time breathing because there's no oxygen? Well, guess what? Your propellers are thinking the same thing. Hey, there's no air here for me to move this drone. So it's hot, it's thin, I need air. There's no air whenever the temperature goes up. The molecules become less dense. This is why everyone tells you that the best time to fly your drone is when the temperatures are cooler. So only taking into consideration just the temperature alone, you understand that it will affect the efficiency of your drone if the temperature goes up. To say it another way, just so you're clear, if the temperature goes up, the efficiency of your propellers will decrease. Okay, so you have temperature under your belt, right? I don't hear any crickets. I hear no crickets. Let's move to the next one, and that is pressure. And you see, I ask a question before I actually explain it, because a lot of people really just tell you about what pressure does, but they never actually give you the definition of what pressure actually is. You see, air pressure is the weight of the air above that is pushing down on you. Always remember that we're sitting under a column of air that extends all the way up to the atmosphere, and the air mass is pushing down on us because there is something called gravity. And this constant pushing down of air is what's called pressure. Now, if I didn't explain that in that way, you would only understand half of what I'm trying to tell you. Pressure can also affect the performance of your drone. Now, listen to how what I'm about to say makes perfect sense. If your drone is closer to the ground, there's more air above it, more pressure. If your drone is higher up in altitude, there's less air above it, so there's less pressure. Do you see how I just made you understand something we're going to be discussing shortly, and that is density altitude? As you fly higher, the pressure drops because the air gets thinner. There's less air. And if there's less air at higher altitudes, that means that the propellers don't have anything that they can work with. So the efficiency of the propellers will decrease as the altitude increases because the air gets thinner. Just as I mentioned to you before about how flying into the wind with an airplane causes the plane to have more lift. Well, that's because the more air that you have around a winged surface means that the efficiency will increase. The less air that you have around a winged surface means that the efficiency will decrease. So when we're referring to pressure at higher altitudes, there's less air pushing down. So that means the air gets thinner and there are fewer air molecules for your propellers to work with. And the third thing that affects air density is humidity. And do I need to explain what humidity actually is? All you have to do is just head down to South Florida and stand out there for about an hour and you'll find out what humidity is. This one actually surprises a lot of people because moist air is actually less dense than dry air. Let me say this again and explain it so you get it. Humid air is actually thinner air. And I know a lot of you just said, hey, we need to check Mike into the mental institution because when it's humid outside, it's just really thick and I sweat like you would not believe. But guess what? Water vapor molecules are much lighter than nitrogen and oxygen molecules. So when it's really humid, the water vapor molecules that are lighter actually push out the oxygen and push out the nitrogen, and the air is actually lighter and thinner than it was when those heavy oxygen and nitrogen molecules were there in the first place. So if the overall air mass decreases, then the result of that will be a lower density or thinner air whenever it's humid. And a lot of you are still not getting it, but let me give you a simple analogy that's going to make you really understand this. Let's say I had a glass jar and I filled it with heavy metal balls. Well, now I replace those heavy metal balls with ping pong balls. Well, guess what? It's the same volume of balls that were in there, but only the glass jar is now lighter because the ping pong balls weigh less. Do you see how I break this down for you? And I'm laughing because I know how difficult it is to understand these complex topics unless you have someone who can break it down simply with simple analogies. So to sum this up for you, temperature, pressure, and humidity will affect air density. And as air density changes, so does density altitude. Hey, listen, if you want me to go deeper on these topics, I will. All you need to do is to post a comment. These broken down explanations on these new series of videos that I'm doing for 2026, 2027 are exactly what we need, not only to pass the Part 107 exam, but to become better remote pilots. And I'm so sorry that it took me so long to get this video uploaded because I was sick for 2 weeks. No one knew that. But I am working on the third video, and that has to do with latitude and longitude. It's a big one. And I'm going to break everything down for you so that way you have a complete understanding and comprehension of what you need to know to pass this exam. Hopefully, you'll get it with a 100% score. So until then, I will see you all on the next video. Good luck with the exam.